Welcome to the deep dive. Our mission for you today is to decode this really notorious trap on the RHCSA exam.
Yeah, it's a specific lab scenario that, well, it just instantly fails thousands of otherwise completely qualified candidates.
Right. And we are pulling this directly from a stack of notes covering episode 38 of the RHCSA series podcast.
Which, just to give you the lay of the land here, is an independent project. It's generated with NotebookLM.
Yeah, completely unaffiliated with Red Hat, just to be clear.
Exactly. And this particular deep dive sits right in the middle of Season 2, so that covers episodes 26A through 50.
It's just a critical slice of exam prep, honestly.
Oh, absolutely.
Yeah.
We are looking at a scenario called Auditing Log Streams, and it is officially rated as high difficulty.
High difficulty. But before we even get into the technical architecture of, why it's so difficult, I really have to set the mood for you.
Oh, the cover art.
The cover art for this is just phenomenal. So picture this. You're looking at a penguin, naturally,
Right, of course.
standing right in the middle of this high-tech, aggressively cooled server room. But this penguin is wearing a remarkably sharp tuxedo with a bow tie.
Classic.
Yeah. He's holding a microphone in one flipper and a cold blue soda can, covered in condensation in the other.
And, that combination of formal precision and just absolute calm execution, that is exactly the mindset you need when you sit down at that terminal.
Which brings up a really common misconception in our field, I think. People often think system administration is just about making things work.
Just getting it done.
Right. If you can get the data from point A to point B, you win. It feels like moving furniture.
Yeah, that's a good way to put it.
You pick up the couch, you navigate the hallway, you put it in the living room, and the job is done.
Right. That's the purely functional mindset. It's discretionary access control, essentially.
Exactly.
If my user account owns the file and I move it, I've succeeded.
But then, you step into the world of enterprise Linux, and suddenly it's not just about moving the couch anymore.
No, not at all.
It's about whether the couch has the proper mandatory access control clearance to even exist in that room.
And whether the invisible security guards patrolling the terminal will even let anyone sit on it.
Yes. That is the transition from basic Linux usage to true enterprise administration.
It's that huge shift from mere functionality to strict compliance.
Because in a home lab environment, moving text around is trivial.
Totally trivial.
Yeah.
But on a production server or, in an exam environment governed by Linux, simply moving text without architectural awareness is a guaranteed failure.
Okay, let's unpack this. Because when I first looked at the brief for this scenario, I genuinely questioned that high difficulty rating.
I think a lot of people do initially.
Right. So the narrative set up for you, the admin, is this. Your security team needs a daily dump of all authentication failures, and they need it parsed from the system journal.
Seems simple enough.
And this data has to live in a specific web-accessible directory, which is var/www/audit reports. So I'm looking at this request, and I'm thinking, why is this considered hard? You grep a log, pipe it to a file in the web directory, and call it a day.
Well, what's fascinating here is that the simplicity of the request masks a massive web of interdependent system services.
Right, it's a trap.
It really is.
Yeah.
You aren't just moving text. You are being tested on a very specific combination of administrative domains.
Like a lot of different objectives all at once.
Exactly. We are looking at Objective 1.2, which is input-output redirection, Objective 1.7, text filtering, Objective 9.1, user management.
Wow, okay.
And the anchor of the whole scenario, Objective 10.5, Linux context.
So if I just slap a file down in that audit reports directory and hope for the best, the security team isn't going to be able to read it.
Not a chance. The web server daemon, so the HTTPD process actually serving these files to the network, it operates under really intense process confinement.
Meaning it's restricted.
Highly restricted. It doesn't matter if you set the traditional Linux file permissions to 777.
Wide open.
Right, wide open.
Yeah.
If you put a file in its directory, but that file doesn't have the exact, precisely correct Linux context stamped onto its inode, the web server's request to the kernel is intercepted.
The invisible bouncer steps in.
Exactly. The kernel drops the request, the web server throws an access denial, and it just acts like the file doesn't even exist.
So we have to build this environment securely from the ground up, starting from a position of basically zero trust.
Yeah.
And naturally, we are doing all of this as the root user. So the very first step in laying this foundation is ensuring the web server software actually exists on the system.
You have to have the tools installed.
Right. And the source notes give us this highly efficient conditional command. It's !RPM-QHTTPD, then DNF install -YHTTP verify.
Which is an incredibly clean way to script infrastructure, honestly.
Yeah, rather than blindly running a package manager install command and just flooding your terminal with dependency checks.
Exactly. You query the local RPM database first. If the daemon is absent, pull it from the repository. It keeps the terminal output clean and really focused.
Makes sense. So once we verify the web daemon is present, we establish the directory structure, just a standard -dir-p var/www/audit reports.
Easy enough.
But here is the pivot that introduces the friction. The security brief requires a specific service user to own this directory.
Right, the log auditor.
Yeah. So we drop in the command usered-s/spin/knowledge-in log auditor.
A very crucial step.
Now wait, if we are just creating this user so there's a name attached to a directory for audit purposes, why go through the trouble of explicitly defining the shell as spin knowledge-in?
That's a great question.
Like if they don't have a password, they can't log in anyway, right? Isn't it overkill?
It might seem like it, but relying merely on a locked password is a massive architectural vulnerability.
Really? Just the password isn't enough.
Definitely not. When you execute a standard user-add command, Linux defaults to provisioning a fully interactive environment. It assigns bin bash or a similar interactive shell.
Okay.
But Log Auditor isn't a human. It's an abstract entity created solely to hold file ownership.
Right. It doesn't need to execute commands, doesn't need to type anything.
Precisely. By explicitly defining spin knowledge-in as the shell within the password file, you are changing the fundamental behavior of the authentication system.
So it blocks them at the door.
Totally. If a malicious actor somehow manages to pivot through a vulnerability, and they attempt to switch user contexts into the Log Auditor account, the system looks at the assigned shell.
And it sees a knowledge.
Yeah, it executes bin knowledge-in, which just politely prints, "This account is currently not available," and immediately terminates the session.
Wow. So it aggressively shuts the door at the shell execution level, rather than just hoping the password hash holds up.
Exactly.
Yeah.
It reduces your attack surface to absolute zero for that account. You achieve the required auditable file ownership without expanding the interactive footprint of the server.
That is so smart.
You are granting the entity exactly what it needs to satisfy the discretionary access control layer and nothing more.
Okay, that makes total sense for the foundation.
Oh.
So we have our bulletproof vault, and we have our restricted daemon ready to serve the files. But right now, the vault is completely empty. We have to actually capture the authentication data and pipe it into this trap we just built.
This is where we transition into the plumbing phase.
The plumbing phase, I love that.
Yeah. And capturing volatile data from a modern Linux system requires interacting with the system journal.
And the command string the nodes provide for this is so elegant. It's journal stl-eehse, pipe that into grep-I failed, and then redirect with a greater than symbol to var/www/audit-reports/sushfailures.txt.
It's a beautiful pipeline.
It really highlights a massive shift in how we handle logs, doesn't it? We aren't just opening a flat text file like varlog secure and hoping the data we need is formatted consistently.
Oh, absolutely not. Legacy syslog parsing is incredibly fragile.
It really is.
You are totally at the mercy of whatever format the application developer decided to use that day.
Right, just a mess of text.
But by targeting the sysded unit directly with journal-usd, you are interrogating the binary journal.
You're leveraging structured, metadata-rich logging.
Exactly. The system journal absolutely guarantees that every single line of output you are looking at originated specifically from the SSH daemon process.
So you filter out all the system noise before you even run your search.
Yep.
Then we take that isolated SSH stream and pass it into our filter, grep-I failed.
Which purifies the stream further, leaving us with only the security events the brief requires.
It's literally like a water filtration system. The pipe operator passes the raw flow into grep, grep catches only the failures, and then the redirect symbol is the funnel catching that clean stream.
That's a perfect analogy.
But the output of that grep command is just volatile data sitting in standard output memory. If we don't catch it with that funnel, It prints to the terminal screen and is gone forever.
Right, it's ephemeral.
So we redirect standard output, file descriptor 1, directly into our target file in the var www directory. We've successfully navigated the data problem.
The text is physically resting on the storage block exactly where the security team requested it.
The functional requirement is met.
But the architectural requirement is still failing.
Because of the invisible security guard.
Linux.
Yes, the Linux trap. If the automated grading script attempts to curl that file right now, it receives an HTTP 403 forbidden error.
Just a hard stop. So let's look at how we satisfy this invisible bouncer. First, we have to align the traditional file permissions.
Right, the discretionary layer.
We run chown-R log auditor, log auditor on var/www/audit reports. We recursively hand ownership of the directory and our newly minted text file to the service account.
Standard stuff. But then we hit the mandatory access control layer. The notes instruct us to run manage fcontext -thttpt as a content, followed by the directory path with a regular expression string.
Right, the quote var/www/audit reports open parent /.star close parent ?
Yeah,
quote.
that regex is a mouthful. But we are defining a regular expression that targets the directory and any child objects created within it.
And we're assigning the specific Linux type context that the HTTPD daemon is authorized to read.
Right. But then we are immediately instructed to run a completely different command. restorecon-RV on that same directory.
Ah, yes.
Here's where it gets really interesting. We already defined the role, and we told the system exactly what context we wanted using Samanage. Why do we have to immediately turn around and run restorecon? It feels so redundant.
I get that a lot. Understanding the separation of duties between those two commands is the ultimate pro tip for navigating Linux, honestly.
Pretty examine in production, right?
Both. It is the single most common conceptual failure. You have to understand how Linux stores its data.
Okay.
Manage if context does not touch your files. It doesn't look at your file system at all.
Wait, really? It entirely bypasses the actual data on the drive?
Completely. When you execute Samanage, you are interacting exclusively with the Linux policy database, which is usually located under etc. Linux targeted.
So it's just updating a database file?
Yes. You are effectively writing a new rule in the architectural blueprint. It's like taking an employee handbook and writing a new policy that says, from now on, anyone who moves into the corner office gets a standing desk.
Okay. But writing it in the handbook doesn't magically make a standing desk appear in the office.
Exactly. The live file system, the actual inodes on your hard drive, are completely unaware that you just updated the master rulebook.
Oh, wow.
The text file you created a moment ago still possesses its default inherited Linux label. It's likely something generic like default or vart.
And the kernel sees that old label and says, nope.
The kernel will block the web server from reading it. That is exactly where restorecon enters the picture.
So restorecon is the enforcer.
It is the execution arm of the policy.
Huh?
When you run restorecon-RV, it parses the master rulebook, evaluates the regular expressions against the live file system, and then physically writes the HTTPDC's content label into the extended attributes.
Exacts.
Right, the ZATs is the file's inode. Without that kernel-level enforcement on the inode, your Samanage rule is just a theory.
Just a piece of paper in the handbook.
Yep. Yeah. The grading script checks the live file system, sees the wrong extended attribute, and fails you.
You have to update the policy, and then you have to force the file system to comply with the policy. You cannot have one without the other.
And you shouldn't assume you've executed either correctly without verifying the state of the system yourself.
Which brings us to the proof of work phase. You have to prove it to yourself before you ever let the grading script or your security team touch it. The source material tells us to use ls-lz on the directory. The -L gives us the long format for our discretionary controls, showing the log auditor ownership.
But the -Z is the crucial flag here.
Right. It interrogates the extended attributes and reveals the Linux context.
And you are looking for a very specific string in that output. You need to verify the user, role, type, and level.
What's the string we want?
The output must show unconfined do :objector : HTTPD size content :S0.
Got it.
The presence of HTTPDC's content is the absolute confirmation that your mandatory access controls are perfectly aligned with your discretionary access controls.
And I imagine seeing that long Linux string populate correctly on the terminal is just incredible validation.
Oh, it's the best feeling.
You didn't just brute force a file transfer, you engineered a secure, compliant data pipeline.
Exactly.
Now, in a production environment, you'd probably just hand off the URL to the security team and close the ticket right now.
Sure.
But in this exam scenario and in lab testing, there is one final, really critical phase, the zero trace cleanup.
Because tearing down the infrastructure is just as important as building it.
The notes lay out a really comprehensive rollback. First, we pull this Linux rule out of the policy database using fcontext-d, targeting our directory string.
Removing it from the handbook.
Right. Then we obliterate the directory and our generated log file with arm-var www audit reports.
Yep.
And finally, we purge the service account and its associated mail spool from the system using userdel log auditor.
If we connect this to the bigger picture, this kind of aggressive, comprehensive cleanup is the hallmark of a disciplined system administrator.
It really separates the professionals from the amateurs.
It really does.
But, if it's just a lab environment or a sandbox server, why is it so critical? I mean, who really cares if a dead service account or an empty directory gets left behind?
Well, because policy bloat is a silent killer of enterprise systems.
Policy bloat.
Yeah. Imagine you are troubleshooting a complex permission denial on a production web server. You create a temporary directory. You tweak an Linux rule with some manage to test a theory about context inheritance.
We'd all been there.
Right. You isolate the root cause, apply the actual fix to the main application directory, and you move on to the next ticket. But you leave your temporary directory and your experimental policy rule behind.
It's just sitting in the database.
Exactly. Fast forward 2 years. A new administrator inherits the server. They deploy a new application into that old, forgotten directory path, assuming default security postures apply.
Oh, no.
But because your custom Linux rule is still lurking in the policy database, any files created in that path unexpectedly inherit contexts that might expose them to unauthorized daemons.
Wow. You have inadvertently engineered a security bypass simply by leaving tech debt behind.
You've compromised the predictability of the server. And the same applies to user accounts. A forgotten account, even one locked down with SPID knowledge in, is an artifact in the password file.
It's a UID that shouldn't exist anymore.
Exactly. It confuses audits and expands the surface area for configuration drift. A disciplined admin ensures that when an experiment or a lab is over, the system state is reverted entirely.
Zero trace means zero leftover risk.
Exactly.
So what does this all mean? When you look back at the entirety of this scenario, this deep dive really illustrates how a seemingly rudimentary task, like literally just moving a list of failed passwords from a log to a web folder, is actually an intricate symphony of enterprise architecture.
It's so much deeper than it looks.
You have to understand the binary nature of systems journal to extract the data cleanly. You have to manipulate standard output streams.
Yep.
You need precise user management to ensure zero trust ownership without opening an interactive shell vulnerability. And you absolutely must master the two-step dance of Linux updating the theoretical policy database and then aggressively enforcing those rules onto the physical innos to survive an automated audit.
It's about respecting the hostile, deeply interconnected environment of a production server.
It really requires a complete paradigm shift in how you view the operating system.
It does. And this raises an important question, I think. Something for you to consider the next time you sit down at your terminal. Think about the sheer scale of modern infrastructure.
It's massive.
The cloud environments you deploy to, the containerized applications you build, the secure banking networks you interact with daily. So much of that foundational security relies entirely on these invisible kernel-level Linux labels, quietly governing every single interaction between processes and files.
Just millions of decisions happening per second based on extended attributes.
Exactly. If a single missing restorecon command can cause an automated grading script to instantly fail an otherwise perfect configuration, consider the hidden misconfigurations in the real world.
Oh, that's a scary thought.
Right. What hidden mislabeled contexts might be quietly blocking critical data flows in the actual servers you interact with every day. The next time an application throws an inexplicable 403 forbidden error, or a file mysteriously refuses to load despite having 777 permissions, Don't assume the application is broken.
Ask yourself, is the invisible security guard in the kernel just doing exactly what the policy database told it to do?
Precisely.
It completely reframes how you approach troubleshooting. You stop looking at the file and you start looking at the kernel policy. Thank you for joining us on this deep dive into the hidden layers of enterprise Linux architecture. Keep your policies clean, always verify your contexts, and we will see you next time.